Thanks everyone for coming. One of the things we're going to talk about today is OpenStack and how Scale Computing's been working with OpenStack and things that we're planning on doing with OpenStack. And specifically what I want to talk about is basically kind of the computing from the data center to the edge and really focusing on some of the edge components. And so first off, so to introduce myself, so I'm Jason Collier. I'm founder at Scale Computing. And a little bit about Scale if you don't know. So we're a company, we've been in business for a decade now, and hard to believe, so it's officially, I don't think we can call ourselves a startup anymore because we've been around for quite some time. We've got 3,000 customers. Majority of those customers are what you would think of as kind of mid-sized organizations, like kind of the 500 to 1,000 employee organizations. But we also have kind of a growing a very much growing business in kind of, you know, things like retail space and where distributed computing and this edge computing piece is really coming in. Now, there's a couple of things that we announced here during OpenStack. Now, our CTO who was here a couple of days ago gave a presentation on basically high performance block with Scribe and Cinder. So Scribe is our underlying storage technology that we developed that is a distributed block engine. So to talk a little bit about Scribe, I just want to kind of highlight this piece. We did some testing with basically NVMe, Intel Optanes, and other SSDs, hard drives that actually run in the system. And one of the interesting things about Scribe, you can mix and match drives of different types in different node sizes from a hardware perspective that can give you different profiles and performance characteristics for those applications. So one of the things that we did was take this engine where we've got the capability, so you can see we've got that QEMU, KVM components over there. Within a single virtual machine, within a single instance, we can define virtual storage devices that can have different performance characteristics. But the good news is you don't have to worry about, you know, what types of devices I have to assign those to. Now, one of the things that we actually did is also take this Scribe component, separate it out from what Scale traditionally is. We typically sell hardware. That kind of the first slide that I popped up. We sell hardware appliances designed for edge compute, but we can also separate that storage stack out and plug that directly into Cinder and get exceptionally high performance characteristics. So for workloads where you have high OLTP expectations for a workload, these are some of the latency components that we tested against. This particular test was running basically near bare metal performance within the virtual machine itself. So we were running about 1.2 million IOPS on these systems where if we're running the Intel, the P3700s, we could get, you know, basically mean latencies of about 116 microseconds. We put that on Optane, we can get down to near the 20 microsecond latencies. Now, I want to kind of preface a little bit about where Scale came from, but also how this kind of transitions into, you've probably heard HCI and this whole hyperconvergence component, where that has actually taken and transitioned into what we're seeing a lot with edge these days. And so, one, where did this HCI term come from? So everybody knows HCI, this hyperconverged infrastructure. What is that? So the original intent, so here's a little piece of trivia. Basically, yours truly, my CEO, Jeff Reedy, and analyst Arun Tanaja actually came up with the word hyperconverged. I still have not received a single royalty payment for that, by the way. And if you're sick of hearing that buzzword, so am I. But what it was intended to mean was the combination of converged infrastructure inclusive of a hypervisor, right? So there became two ways within the industry in which to get HCI. One is called HES, which is hypervisor embedded storage, which is what we are at Scale. that means there's effectively no virtual machine in the data path. A lot of our backgrounds came from high performance compute. So what we did is we built this distributed block engine that runs down at the kernel level. This is also known as kind of the in-kernel virtualization component. And then the other way to do that is the VSA, virtual storage appliance. That's where you take, guess what, the capabilities of a SAN, you take that, put it in a virtual machine, you run that on top of a hypervisor. So the biggest difference between HES and VSA is in HES, basically, in this particular case, we control the hypervisor does not control us. The problem that we were trying to solve with hyperconvergence was the complexity of what modern virtualized infrastructures look like. Now, I understand a lot of your infrastructures probably look a lot more complex than this, but I wanted to basically take this, pare it down into basically a simplistic component. And when you build this from the bottom up, so you'll see, typically you're going to have some type of shared storage mechanism underneath. There's some type of SAN that typically has a file system layered on top of it. Then there's a series of LUNs that are then mapped out. They hook into some type of virtualization platform. And when you get down to it, you know, a LUN or a data store, anything like that, is an object file that, guess what, sits on a file system that's mapped across a RAID set. So when you actually look at the data paths that it takes when you're up in a virtual machine, you got an application, you need to take and write a 1 or a 0 to a disk. Well, what's actually going on? You're going through like at least 7 hops of a file on a file system, on a file on a file system, on a file on a file system, mapped across a network fabric, sitting on a file system, mapped across a RAID set. And that's the complexity that is happening from the underlying hardware perspective. So I thought long and hard about a good way to actually diagram out what this looks like, and this is the best diagram that I could come up with. That's what the hardware looks like underneath. And so the reality is, how do you get to root cause analysis when something goes wrong in that hardware, right? Maybe you poke the bathtub, move it a millimeter to the left so that the bowling ball drops, hits the diving board, the guy jumps into the bucket, so you can do what? Catch the mouse. What is catching the mouse in everything that we do? It's keeping those applications that make the business make money running. That's our goal in IT. And guess what? There's a better way to do that. There's a simpler way to do that. There's a better mousetrap, and it comes down to simplicity. So I'm a bit of a nerd, and one of my pastimes is sitting back and reading internet RFCs. One of my favorites is RFC 1925. It was written by Ross Callan back in 1996 when he worked for DEC. If you can notice the date of this is one of those April Fool's Day jokes, right? The 12 networking truths. And there are a lot of funny truths that are in here, but there's a lot that are golden nuggets. So when you take and you come back, you look at this, guess what? Truth number 8, it's more complicated than you think. My favorite, and what we strived for at Scale, was truth number 12. In protocol design, perfection has not been reached when there's nothing left to add, but when there's nothing left to take away. So when you go back and you look at the complication of a modern virtualized infrastructure, you see all these files on file systems on files on file systems, and you ask yourself why. Is there a better way? So if we took a clean sheet of paper approach, what would we do? And when you think about this, like SANs, they were never designed for virtualization. They were designed to run shared databases 30 years ago. And going in and using that to try to solve a problem is like using a screwdriver to pound in a nail. Will it do the job? Yeah. Is it the best tool? Probably not. So what we did is looked at this and eliminated everything in the stack that we did not need in that process. So in doing that, when you look at the I/O path that we have created in what we did when we stripped out our architecture, we basically got a 60% improvement in the software stack alone in the number of hops that we need to make across files on file systems. In fact, in a scale and a scribe-based system, you only basically need 3 hops to basically commit a 1 or a 0 to a disk. So that's a 60% increase in efficiency. Now, to talk about some of the other components and ways to do this, and ways that in which other people are going through and trying to solve this problem. Truth number 5, guess what? It's always possible to agglutenate multiple separate problems into a single complex interdependent solution. And guess what? In most cases, that's a bad idea. Does anybody know what this is? Or this was? This was the world's largest Rube Goldberg machine. It was built by guys down in Purdue University when there was a contest for that. And I say it was because let me show you the VSA-based approach for doing HCI in the I/O path. And if you actually take a look and you trace that I/O path out on what needs to happen, if you've got a virtual machine that needs to commit a 1 or a 0 to a disk, you're going to find out that it's going to be no less than 14 hops across files on file systems to go through and commit a 1 or 0 to a disk. So when you look at that, guess what? Not all of these HCI solutions are created equal or efficient. Trust me, this is going to tie back into the edge component. I like analogies, so let me just say that the Scale HES approach to efficiency, if you want to go out and build a deck on the back of your house, you can go down to your local home improvement store, take your pickup truck, load it up full of wood, drive back home and build your deck. The VSA approach starts out a lot the same. You take a pickup truck, you load it up with wood, then you take that truck and you load it in another truck, and then you load that on top of another truck. Not exactly the most efficient. Now, why does efficiency of that stack matter? And it matters because of the things that are here, but more importantly, the things that are coming. So NVMe, non-volatile memory express. The difference between NVMe and the way that we have been doing storage, the entire history of storage technologies, is controller-based architectures versus controller-less architectures. So the best, once again, analogy that I like to describe controller-based versus controllerless, it's the difference between boarding a plane, which I'm sure we all probably did when we're coming to the conference, versus boarding a train. How does this translate? It translates into latency. So when you're boarding a plane, you got one door, and all the 1s and 0s have to walk up that staircase, go through that one door, find their seat, and sit down. Now, the bandwidth and the capacity is all there on that plane, pretty similar to what's on a train. But guess what? That train pulls up to the station, doors open, many doors open, 1s and 0s get off, 1s and 0s get on, everybody sits down, the train takes off. Latency. The time it takes to board a plane versus boarding a train, significantly less. Now, let's translate this into actual real world numbers. And I'm going to use AHCI, basically just Advanced Host Controller Interface. Simple, what you would have in your laptop if you don't already have NVMe in your laptops, right? So when you look at this, I'm just going to focus on that first line, max queue depth. AHCI. You've got one command queue. You got one door. And then you got 32 commands per queue. You got 32 people that can stand in line to go through that one door. With NVMe, the train pulling up to the station, you got 65,535 doors, and 65,536 people can stand in each one of those lines. Latency. Now, if you take a storage subsystem today and you compare just the full-on, here's what's today, AHCI versus NVMe, you're going to find out that guess what? You put NVMe in anything with no optimization, it's going to be a heck of a lot faster. However, you notice I've got that software stack component up there. This is the first time in computing history the storage has not become the bottleneck. So having an efficient software stack becomes important. Now, if we take and we compare that VSA to the HES approach using today's storage technologies, it's a little faster, right? HES is a little bit faster. You notice the software stack components, you'll see the blue. You actually won't see it over there on that because the latency drops if you've got a very efficient software stack. Now, you take and you combine VSA and HES and you put them on NVMe. What happens? Where's the bottleneck? It's not the hardware. The first time since this entire industry has started from the mainframes that, guess what? The hardware on storage, data storage, has not been the bottleneck. So everybody's been hacking away at solutions, software solutions, have been hiding inefficiencies within the software stack. And this is why efficiency matters. And here's why. Does everybody know what this is? It's a ruler, right? Does everybody know what this is? It's a ruler. This is just Intel's version, though it doesn't have the little like graduations on it though. They should probably put those on there just as a marketing gimmick. Why does this matter? They actually announced this a couple of weeks ago. The roadmap to, guess what? 1 petabyte in one rack unit. 1 petabyte in one rack unit. Now, how much do you think efficiency matters in that stack? If you've got inefficient software running that much capacity in a single node, you're going to have issues. Back to RFC 1925. It's my little transition to the edge component. There's a lot of technology changes that are happening that are very influential in this industry. Truth number 9, guess what? For all resources, whatever it is, you need more. And truth number 10, one size never fits all. So let's talk about OpenStack plus Scale gets you, guess what? Hybrid cloud. Hybrid cloud in the fact that you can have your data center, your core cloud components, private cloud, public cloud, whatever it happens to be, tie that into the edge compute resources. Think of running these little edge devices, these edge micro data centers out there that effectively become cells plugged into Horizon that become Nova resources that you can go out and utilize from a remote perspective. Now, one of my other RFC 1925's truth number 11, guess what? If you've been in this technology industry for, 20, 30 years, you will probably have seen many of these things before. It's a very cyclical industry. In fact, it's cyclical enough. Most industries themselves are very cyclical, but technology, man, you see these cycles happen more often than not. The truth number 11, guess what? Every old idea will be proposed again with a different name and a different presentation, whether or not it ever worked in the first place, right? So here's cloud circa 1964, right? We used to call it time sharing on a mainframe. What was edge back then? Guess what? So here was that mainframe. Here's that big, here's your IBM 370s, 360s, 380s, 390s, the Z series. And guess what? Then that came out the AS400. What was that? That was basically an edge appliance that was built to basically offload processing down at that piece. And one of the things that I have determined after my years in the space, the technology relations that we have actually had, is the fact that, guess what? There is no cloud. It's just somebody else's computer. I've been to Google's data center. You know what's in it? A bunch of computers, right? And everybody always thinks about on-premises versus the cloud. And that's not the right way to think about this. It's on-premises plus the cloud. That's kind of the ultimate answer that we always seem to be searching for, yet we just seem to be on this pendulum that swings back and forth between, oh, it's all this, it's all this. So one of the analysts, so Alistair Edwards with Canalys, he said, guess what? The 2010s were all about cloud computing, and the 2020s are going to be all about computing at the edge. The 2020s trend will be hybrid cloud, public cloud plus on-premises. On-prem will be used for reasons of, guess what? Latency, control, compliance, and cost. And guess what? Micro data centers at the edge will be replacing traditional rows and rows of racks at these centralized data centers as an area of explosive growth. Guess what? Those key vertical markets are going to be government, retail, manufacturing, healthcare, transportation, and agriculture, or pretty much most of the verticals. Truth number 2, no matter how hard you push and no matter what the priority, you can't increase the speed of light. At least we haven't figured that out yet. Be exciting when we do. And to quote my CEO, like, guess what? When microseconds matter, the cloud's only 88 milliseconds away. So going to that one latency issue, let's talk about latency. One of my favorite companies to talk about is Tesla, because they have really cool technology. They've got a lot of different ways in which they utilize technology that really hasn't been, let's just say, it's been thought of before. It's never been implemented the way they've done it. One of the interesting things is the whole LiDAR system that controls basically the automatic braking. They've got this LiDAR system, they got cameras, they got all these series of sensors that know everything that is going on around you. And it can see several cars in front of you. There's a YouTube video of this Tesla going along, and here's this car that stopped. It brakes before the car in front of it brakes because of the auto braking system. The car in front of it hits that car, and the Tesla stops in time. Now, that's a latency-driven decision. Would you like that decision to be made in the cloud if you're driving that Tesla, right? So the sensors come back and they say, hey, we're sensing an anomaly. Hey, cloud, what should we do? Just a second, let me make an LTE connection. And send that up. Cloud, do you think I should stop? Cloud's like, wait, I got other priorities I'm dealing with right now. Okay, yeah, okay, let me calculate. Yeah, you should probably stop. LTE connection comes back down. Boom, right? Too late. It's a latency-driven decision. This is why edge is going to be crucial to solving a lot of the problems that we've got out there. Another cool thing about Tesla technology, has anybody here in the room been in a Tesla when autopilot is engaged? Isn't that just the coolest, just weirdest thing? The very first time you're in it, you're like, it's scary, right? Because my friend, he like backs out of his driveway, he's like, check this out. He like engages autopilot. We're on like side streets, pulls up to a 4-way stop, it stops, it goes. He's like not touching anything. We merge onto the freeway. It goes through, takes us to the destination where we were going, never touched it the entire time. And I thought, wow, that's some pretty cool technology, all based on AI, neural nets, learning to drive the car. But guess what? Bad things can happen. On our way home, like we're sitting there, autopilot's going, and here's this big semi that pulls up to us, starts to merge over. He's like, whoa, so he pulls the wheel over, hits brake. Well, what happens in a Tesla when that does that? Well, what happens is it takes the 30 seconds before and the 30 seconds after you gave user input into that system. It's the IoT device down here. It takes the 30 seconds before and after, takes that data and uploads it to the edge. The edge then processes the data that is relevant to what happened to avoid that collision. It will then upload it to the cloud where it goes into the process of retraining that neural network. By the time we get home, we plug in, it has already uploaded the data for the new neural network into the system. And it does that by permeating back from the cloud down to the edge, down to those individual things. Because when you look at this, that's not an impressive diagram. Now imagine millions of cars out there having multiple of those interactions a day. How much data is that? Edge is crucial for filtering out the components that you don't need. Now, one of the other things that Alistair said, he's like, the focus of IT is like this pendulum that swings. between centralized and distributed models. He's like, and we're now moving back towards the distributed model. I agree with his observation, but that's not where we need to head. When you think about that pendulum, and you think about that swing, we have been dealing with this pendulum swinging back and forth in IT for quite some time. Between centralized, and then we swing to a distributed model. And when we think about the application, mainframe, and then we swung over to distributed to the PC. And now we're talking about, let's take everything to the cloud. And it's going to swing back to the edge. But when you stop winding that clock, where does that pendulum stop? At a cloud unity. It's not one or the other. It's both at the same time. One of my good friends, Mark Thiele, if you folks are familiar with kind of data centers and building out big data centers, he's one of the guys that helped build out SuperNAP down in Las Vegas, you know, one of the largest data centers on the planet. And his definition, guess what? The edge is where a combination of technology use requirements creates a location-specific requirement to meet a set of customer use case needs. Those customer use case requirements could be a combination of any or all of the following: latency, data sovereignty, security, performance, cost, and reducing impact on the backhaul networks. One of our customers that has an edge solution deployed is the 6th largest grocery store retailer on the planet. It's a company called Ahold Delhaize. They're headquartered in Belgium. They have 6,700 stores worldwide. What do they have in those stores? They're putting that in. That is a micro data center sitting at the edge. That is scale computing hardware running on top of that. See, we've got that is basically, you know, an 8 rack unit case. We've got 64 cores, 512 gig of RAM in that. It's not overly big, but guess what? It runs what those grocery stores need. Now, guess what? A lot of those grocery stores don't even need that. And some of the things that we have in dev and testing are things like, guess what? Intel NUCs. Now, my goal is to get these little NUCs down to a price point of, I can take 3 of these, put them in a cluster, have a clustered solution that could then also plug into OpenStack as one of these edge compute cells. But I want to sell that thing for less than $5,000 for a cluster of those. Already what we've got back here, that is probably about a $50,000, $60,000 cluster. That's 10 gig on the back end of that. I can run probably 200 virtual machines on this little platform that I, guess what, can unplug. I got APC UPS in there. I can unplug that thing, roll it around. I got 17 minutes of battery runtime. I got a Cradle Point LTE connection on top of that. That is a data center in a box I can pull out into a parking lot and still have access to all that data. And we've also got all the capabilities of doing replication between sites. And we can take this down as small as, guess what? We've got our stuff running on the compute cards. Now, these aren't overall very large resources, but this thing is literally the size of a credit card. It is tiny. It's got, and when you think about how small it is and the resources, I mean, this thing makes a Raspberry Pi look big, right? From a size and form factor perspective. If you're talking 4 gig, I can run, I actually had I got one set up in my lab where I've got 4 virtual machines running on this thing that literally is the size of a credit card. I can take it and pretty much plug it into anything, digital signage, whatever it happens to be. Edge is going to fundamentally change, you know, the way that we think about doing this compute. And I think taking and plugging that into the orchestration contents of OpenStack, and for the folks that are out there running OpenStack, this is going to give you a fundamental capability of taking the data center and extending that out to the controls of all these edge components. Think about Now you think about your computing resources, you think about your computing resources in the data center, what you've got there. Now think about all those remote locations, especially like think about retail, think about, think about oil and gas, think about all those places where you have got all of these independent sites that you have to manage. Now imagine pulling that all under OpenStack and being able to aggregate all of that compute power as one big resource that you can utilize. And that's what we're doing at Scale. And we are looking forward to pushing forward with our initiatives that we're working with on OpenStack to get our stuff to be an effective cell that you can manage within that OpenStack component. And that's all I got. Any questions? Question? Yeah.
When you distribute your data, it's across all the nodes in that particular form, right? Not across this.
It's in that, so it's in the nodes that happen to be in that cluster, but then we've also got the capability of doing up to 5,000 snapshots per virtual disk per virtual machine that then can be replicated to a remote cluster. And we can do timing down as far as basically doing, I think, 1-minute snapshots. Of those, and those are, effectively kind of VSS synchronized integrated snapshots that can be done. There's a lot of different ways in which we can utilize those snapshots. One of our partners that we're doing that with is actually Google, where we can run these scale clusters up in Google Cloud Platform, and we're doing replication. One of our customers that was actually using this was doing beta on our implementation into Google. They were doing, kind of snapshotting asynchronous rep. Still, when we were in beta, the hurricane hit. Pretty much wiped out Puerto Rico. So they're like, okay, we know this is still beta. We're failing this over to our production because we have no other option. So they are still running all of that stuff in GCP. So if you're in Puerto Rico and you go to a Wendy's, every hamburger that you buy is being processed through a Scale system that's running up on GCP. It is a copy on write, Maltman? Yep, copy on write. Yeah.
What kind of virtuals are you running in your cluster?
What was that?
The retail use case.
Yes.
What kind of VMs running?
They are running inventory control, point of sale, and then doing, probably about 10 to 20 VDI style of instances on top of it.
Are they all in the kind of OpenStack?
They are currently not in OpenStack. They're actually all running that under the Scale interface right now. Any other questions? Yes?
Microphone, please. Please use the microphone. Being recorded.
Oh.
I want to know, is there any acceleration requirements at edge node?
As far as acceleration, any type of, okay, so acceleration as in any particular type of acceleration you're looking at? Like
such as GPU, FPGA, and so on?
Currently, no, but we've got those running in the lab right now as well. So for the micro data center, we're going to be able to do that. As far as the edge, the really small edge nodes, there's a possibility that could happen. I know right now those the latest iteration of those Intel NUCs are running some AMD cards, but I don't know if they're doing anything like the NVIDIA vGPUs to do that type of graphics acceleration currently. So I don't know on the really small stuff. We've got the larger stuff running in lab right now. We haven't productized it to a point, but it's good to note that that's something of interest. We've been getting on that a lot lately.
Okay, thank you.
Yeah. Anyone else? All right, well, thank you. Thanks everyone for your time. Looks like we'll get out a few minutes early, about 5 minutes early. So enjoy the rest of the OpenStack Summit. I know it's been a great show for us. So many great people here to meet, so many great companies, other vendors to talk to, and yeah, definitely enjoy your show, enjoy your time in Vancouver, and safe travels back home, everyone. Thanks so much.